Okay guys, so I want to talk to you about using Riemann sums, and the reason I want to talk to you about using a Riemann sum is because they're used when you're calculating the definite integral. Okay, so in case you don't remember, which is totally fine, a Riemann sum occurs when you're adding the same formula essentially over and over and over again. So when you were in Algebra 2, you probably saw Riemann sums denoted with this big sigma, which is the same. And then you had some letter here like k equals 2, and then some number on top. So for this example, we're just going to do 5. And then you had a formula. So in this one, I'm just going to do x to the power of k. Okay, so hopefully you remember that this is equal to x squared, because that's my first value of k, plus x cubed, plus x to the fourth, plus x to the fifth, and I know I'm going to stop at the fifth power because that's what is on top of my Riemann sum. Okay, so whatever that is, that is your Riemann sum. So instead of writing out all this work, you can denote it in this simple manner. Okay, so it's pretty easy. Now, the reason they happen in calculus is when you're dealing with an integral, for example, so you want to calculate the area under the curve from some point A to some point B, right? And as you saw in class previously, the way to do this is to partition your curve, or you want to partition your interval to estimate the area using either rectangles from the left, the right, the midpoint, or a trapezoid. So let's go ahead and partition this curve, and I want to keep it really broad here. So I'm not going to use a number. We're just going to say that we're going to create n partitions, n being some number. So I just zoomed in. So let's say we're going to create one partition there, another one there, and remember all your partitions always have equal width, so even if mine don't, you're going to pretend. Okay, now I obviously drew the partitions so you could see them, right? So they're wider, and obviously that's a countable number. But if I drew in more partitions, they'd be harder to see. Okay, so we're going to label each partition. So we can call this partition x1, this partition x2, xk, xk plus 1, x to the n minus 1. Okay, so I've labeled it. So now I have n partitions. In my interval a comma b, and I'm using closed brackets because in this case my endpoints are enclosed. Okay, so then if you were going to use a rectangle approximation here, we know that the width of our rectangle, it is the width of this partition, okay, or the width of this partition. It doesn't really matter. They're all the same partition. So any of these partitions have width, and we're going to say that this width, just for notation's sake, is the change, right? Delta means change in our partition, excuse me. So it's the change in xk, essentially, because I just picked xk, okay? So I know then that's my width of my rectangle, and I know that my height is based on, like, let's just do the midpoint, right? I'd find my midpoint and I'd go over to my y-axis, right? So let's call this midpoint on the x-axis, let's call it ck, because it's some value, some constant for c in the interval xk comma xk minus 1. In case you haven't seen this notation before, this epsilon means contained in. Okay, it's a lowercase epsilon. Anyways, so you know then that if your x value is c sub x on your x-axis, then the height is based on this function, right? So the actual height of your triangle, your height is f, right, your function value at some c of k value. So using that notation, you know then that the area of your rectangles is your function value, right, your height of your rectangle times, let's go back to my blue color, the width of your rectangle. So the reason this is important and this formula is important is because it allows you to calculate the area of this whole curve by just using this formula inside of a Riemann sum. Okay, so let me zoom out so I have a little more space to write. Okay, so we already said using this notation, whoa, sorry, that's not what I meant to do. We already said when we're using this notation for Riemann sum that it works when you're adding the same type of thing over and over and over again, right? And if you partition a curve, you're adding the same type of formula over and over and over and over and over again. Okay, so that's why we're using Riemann sums here, because it's easier in terms of notation and it's more correct notation to calculate your Riemann sum. So I could say then that the area under this curve can be approximated by the sum from k equals 0 to n, right, if I had n partitions, of the area of each triangle, and I know my area of each triangle is this formula. So f of c comma k times delta x to the k. So that's why I started off by explaining to you what a Riemann sum is, because the formal notation for partitions under a curve uses a Riemann sum. And again, this is just the height of your rectangle, and this would be its width. So in class, what we're going to look at next time I see you guys is what's going to happen when we take each of these partitions and make it smaller and smaller and smaller and smaller. Okay, so we're essentially taking the limit as these partitions approach 0. Not the number of partitions, but the limit as the width of each partition approaches 0. And that's going to lead us into our formal definition of the integral. So please write down if you have any questions on this, and I will come back to it next class.